Hello everybody. In the last class we learned basics about diode operation, and we also saw how rectifiers can be made using diodes. In today's class we are going to see some more circuits based on diodes, namely clipper and clamper circuits. Okay, what's a clipping circuit? So a clipping circuit is nothing but a wave shaping circuit which controls the shape of the output waveform by removing or clipping a portion of the applied voltage. That means you have certain input voltage. In the output, some part of the input waveform will be clipped, okay, or it will be restricted to some value. Okay, so a half wave rectifier is can be called as an clipping circuit where the negative cycle is clipped, right? So also the clipping circuits are also referred as voltage limiters, amplitude selectors, slicers, and all these are the various names. So there is a lot of applications of these kind of circuits also in the real life electronic devices. So we'll try to learn the clippers first, and then we'll move on to clampers. Okay, so thumb rule for analyzing any clipper circuit or for design of any clipper circuit is we have to first diode can be either in the forward biased or in the reverse biased in these circuits. So whenever it is in forward biased, we will assume that it will act like a closed switch, and when the diode is reverse biased, we will assume that it will work as an open switch. So if you use these two rules, then we will be able to analyze all the clipper circuits. So here is the first circuit which we are going to discuss, which is known as series positive clipping. Here positive clipping means the positive portion of the input signal will be clipped to 0 in this case. So if you see here, the diode is placed with the cathode towards the input. Okay, now during the positive half cycle, this diode will not conduct, and hence there won't be any output, whereas in the negative half cycle this diode conducts here, so it will act like a closed switch. So in the positive cycle it is an open switch, so there is no output, and in the this is an waveform which corresponds to an ideal diode characteristics. Okay, so in the negative cycle this is short circuited, that means it is in a closed switch position, so you have the entire voltage being reflected at the output. So this is the output waveform. So this will be known as series positive clipping circuit. Okay, now you could also have a series negative clipping. Okay, in the negative clipping, negative clipping means the negative portion of the input signal will be clipped. Okay, we should not see this. Okay, the output is positive and call this as a positive clipper. Okay, what it means, negative clipping means, is the negative portion of the signal is being clipped here. So here, whenever the signal is in the positive, signal is going into positive domain, you will find this diode is a closed switch, and hence the voltage is available at the output, and in the negative cycle this diode is reverse biased and nothing is available. Okay, so this is nothing but a half wave rectifier, right? So this is known as negative series clipping. Okay, now you could also have an shunt clipping. So here if you see this, this is the load resistance and this is the diode which is placed here. So during the positive going cycle, this diode will be forward biased. Okay, and we know that during here that this diode is not taken as an ideal characteristic. So both ways. So it depends on for your examination point of view, it will be specified whether you need to consider this diode as an ideal diode or as a real diode. If it is you are considering it as a real diode, then there will be some 0.7 volt here. If it is an ideal diode, then it will be 0. Okay, so during the positive cycle, you will find this diode is forward biased, so you have 0.7 volt, and in the negative cycle this diode is reverse biased, so this is not available here. So the entire voltage which is available here, okay, that is available across the load. Again, so this is the waveform. So the negative cycle is getting reflected here. Again, we are assuming RL is much greater than R1, so the entire voltage is available in the across RL. Okay, So this is known as shunt positive clipping. Again, you could have an shunt negative clipping. Here again you have the diode connected in the opposite manner, where the cathode is connected to the top of the signal here. So now if you see, during the positive cycle, this diode will be reverse biased, and hence the entire voltage will be available. In the negative cycle, you will find this diode will be forward biased, and only 0.7 volt will be available across the diode, and that will be available across the diode, so minus 0.7. So this is known as shunt negative clipping. Okay. Now the diode in series clipper clips any voltage that does not forward bias it. Okay. So that means this is a diode, and now if you see a square pulse is applied here in this particular case. So when it is forward biased, so that it allows that signal to pass, and that is in a series clipper, and when the diode is reverse biased, it's not going to pass anything, so you have nothing available here, right? So the shape of the signal doesn't matter. So this is a triangular shape, this is again a triangular. Here again in this particular problem, the diode is considered to be an ideal diode. Okay. So the reverse polarity less than 0.7. Okay, if you have to consider it as a real diode, then we got to cater for the forward bias. Whenever the input signal is greater than 0.7, only then it will conduct. So that need to be taken into consideration if we are talking about an real diode. Okay. Now we can also have something known as biased series clippers, where you have some additional bias available here. Now if you see here, 5 volt is available out here. So when I am giving a 0 volt, okay, when the signal is at 0 volt, still this diode is conducting, because already plus 5 volt, it is forward biased by plus 5. If the input voltage is minus 1, still it will be forward biased. If it is minus 2, it will be forward biased. So it will be so the output will be available here. So as long as in the negative cycle, only when the signal drops to minus 5, okay, this diode will have 0 across it, and it will get switched off. Okay, again we are neglecting that 0.7 in this case also. So if you see, if I see the waveform out here, see this is the waveform when the signal is going to minus 5. This is the input signal. Till the signal is going to minus 5, now okay, only then the output voltage is available. It gets clipped then. Only till then, till the voltage is, see, it is from the signal is from 0, it's going, it's coming here to the time is t/2 now. Again the voltage is dropping, and it is coming to minus 5, and that is the time the signal becomes 0 out here, right? So the output voltage, so it is the total conduction time is more than t/2 here. Like from here, this is 0. This is slightly, this y-axis corresponds to 0. So here it is slightly before 0, and here it is after t/2. Okay, that is because if you draw a line out here at minus 5 volt, so this minus 5 volt will be reached before 0 and after t/2. So that is the reason it is shown like this, and the maximum voltage out here that it would reach here would be 20 plus 5. Now because you are biasing it with additional 5 volts here, so the maximum voltage here will be 25 out here, right? And the voltage when this input signal is 0, you will have 5 volt here. Okay, so this 0 and this 0 corresponds to 5 and 5, and in the input signal of minus 5 and minus 5 corresponds to 0 in this waveform. Okay, so this is known as biased series clippers. Similarly, in this case, it is negative biased. The diode is in the here it is negative biased, and this is positive biased. So if we see the polarity of the signals, okay, which is different out here. So this diode is placed in the reverse direction out here, and there is a positive signal which is given here, which is known as V. Now when the input signal goes high, right? So so if you see here, so this is the input signal. So when the input in the negative cycle, okay, here let's discuss this. So in the negative cycle, when the signal goes beyond minus V, this diode gets forward biased, okay, because this is biased with minus V volt. So you will have the output signal, you have the replication of the input signal here, right? There is no addition of minus 5, the same input signal gets replicated, whereas the input signal for all other conditions, okay, this diode is reverse biased, and this goes out of the loop. Once it goes out of the loop, the supply voltage which will be available across this terminal will be a minus V. So it is a minus V here. It is a minus V here. Okay, understood? So initially the signal is 0, right? If it is a 0 out here, right? So see, this signal is 0 out here, but this is already negative is given out here. So this diode remains reverse biased, right? So it is going so since it is 0 here, and you have so this diode is reverse biased, so this diode is not in the loop. So this minus V volt is available here, minus V is available here, right? So when this signal goes to the maximum, it continues to remain reverse bias, and then it comes here, and when it follows it falls to minus V, that is the time. Now this is negative here, this is less than minus V here, less than the minus volt which has been used to bias this voltage. Then this diode starts conducting, and then now the input voltage is replicated at the output. So you have for a small duration of time, again when the signal is going to its negative peak and again increasing beyond minus V, this diode gets switched off and you have the output here, right? So this is again the same case out here. If you see here, in this diode is reverse bias. So when this signal is going initially it is 0 out here, right? As it keeps going, and if it goes beyond the V voltage, this diode gets reverse biased. So the moment it goes beyond V, it gets reverse biased, okay? So this goes out of the loop, and once this goes out of the loop, the maximum voltage available here is V, so it gets clipped. Whereas when this voltage is below V, okay, this diode is forward biased, and hence the output replicates the input signal. So whenever the input signal is going beyond plus V, this diode gets reverse biased, and this input signal is isolated from the output, and it gets clipped with this voltage which we are applying here. So this is known as positive biased and negative biased clippers, okay. So you could have a combination clipper also, where this is the input signal out here, and then you have two voltages which are applied across in series with two diodes, both in different polarity. Now see what happens during the positive going cycle. Okay, so this diode initially is off, right? As it keeps increasing, when it goes beyond V1, this diode switches on and the output gets clipped to V1. So at V1, so it goes like this and gets clipped at V1. Similarly, in the negative cycle, initially this is reverse biased, and then when the voltage falls, this diode is already biased with negative minus V2, right, from here to there. So when it falls below minus V2, this diode switches on, and the moment this diode switches on, the output gets clipped to V2. So the signal goes from here, it gets clipped to V1, and then again it follows here, it gets clipped to V2. So the peak of these two signals will be V1 and V2, the output waveform. So we are clipping both on the positive and the negative side, and that is why we call it as a combination clipper. Okay. Now there is something known as Zener diodes also. So we will not get into too much of a mechanism of Zener diodes, but like we said, the diode breaks down when we given certain negative voltage. Okay, so Zener diode works on avalanche breakdown or Zener breakdown, where when you give a certain negative voltage known as the Zener voltage Vz, so that will be the rating of the diode, then the output voltage remains constant here. Here if you see the curve, and the output voltage remains constant, and then it can provide a range of current while maintaining the output voltage across the diode as Vz. Okay, now first thing, the Zener has to be reverse biased, and the applied voltage has to be on a Vz or slightly above that. So the moment this diode gets triggered, the output terminal voltage will be Vz, and as long as you are maintaining a current of within this range, okay, it can provide this range of current with the output voltage remaining constant. So that is known as an regulation effect. Okay, that's how Zener regulates the voltage. So this is the symbol for the Zener diode. Now for example, now this is an input voltage which I have given. Okay, I have a series resistance and I put a Zener. Okay, if this suppose the input is 10 volt and Zener is 6 volt, right? So so if I connect it like this, then there will be 6 volt across this Zener diode, because this Zener rate is rated for 6 volt. Okay, now the value of RS should be put in such a manner that the current is in here, like 10 minus 6 divided by RS should be between 1 milliampere or the maximum Zener current which is this can handle. So as long as that condition is met, this voltage will be around 6 volt. I am applying 10 volt here. If Zener is 6 volt, I will get 6 volt. The value of what should be the value of RS? It should be within this range. Okay, so 10 minus 6, that is 4, divided by RS should be between 1 milliampere, and this is the maximum, the minimum and maximum rating of the Zener will be specified by the manufacturer. Okay, so if you see the data sheet of the Zener, you will get that. So as long as that current is within this range, okay, the output voltage will continue to remain. So you can ideally somewhere in between you will take a RS value which is somewhere in between these two. Okay, so exactly in between. Okay, why do we take it in between? Is now when you connect a load resistance, if the load resistance changes also, right, it will continue to maintain this voltage. This voltage will be 6 volt irrespective of the resistance, change in resistance. Okay, again the resistance should not be changed to an extent where the Zener operation itself is disturbed. Okay, this change in resistance, because when you change this resistance, some current will flow in IL, right? So the voltage, so you should apply a voltage of more than so there will be finally the current in the Zener, this voltage will continue to remain constant. Okay, so you can change the value of RL, so some current will flow into RL, but the range cannot be so enormous that the current flowing through the Zener comes out of this range. Okay, so that is why if you maintain within that range, it will work as a regulator. Okay. If you see, this is an input voltage which is given here, this is the output voltage. So it's a combination of Zeners and diodes have been used here. So if you tap the output from here, this Zener is 10 volt, so you will get an 10 volt. If you tap it from here, while this diode is forward biased, so you will get 10.6 volt. So if you tap the output from here, since this Zener is 3.3 volt, so 10.6 plus additional 3.3, 13.9, and this is the total voltage which will be available here, that is another 5.1 volt, so 19 volt. So here probably you can apply say 20 volt, and there is an RS here. Now even if the input voltage fluctuates, okay, still these voltages will remain constant. So that is known as regulated output. So irrespective, even if this input voltage fluctuates up and down, okay, so it's from 20 it goes to 21, it comes to 18, so these voltages will remain same. Like suppose for an automobile regulator, you have an DC dynamo which is coupled with your engine. When you are giving your accelerator, okay, the engine RPM increases, so this output voltage will increase and it will also decrease, right? But you don't want you want a constant, say 13 or 14 volt, output, so that your bulbs and horn and all, they suppose they are working at 14 volt, you don't want the intensity of the light to change with increase and decreasing of your accelerator. So this is the input which can be coupled to the from the generator which is being driven from the engine. So any variation of this input voltage doesn't get reflected as change in output, okay, because these are all, they act like an voltage regulators. Okay, so this is a little bit about Zener diodes. Okay, now why I introduced Zener diodes? So Zener diodes also can be used as clippers. Now so if you have a Zener diode which is connected like this, during the positive cycle, this Zener as soon as the Zener voltage is reached, okay, it will get clipped at Zener diode. But in the negative cycle, this will act like an forward diode. Okay, so 0.7 volt, which is the forward voltage for a diode. So it will get, in the negative cycle it will get at 0.7, and in the positive cycle it will get clipped to Vz. So that Vz will be the specification of the Zener. Similarly, if you have two Zeners which is connected back to back like this, so during the positive cycle, this Zener will get triggered actually, so it is Vz, and in the negative cycle the bottom Zener will get triggered. Okay, if I have to be more accurate, this positive diode will get in the positive cycle, the bottom Zener is going to get triggered, because the Zener is connected in this. The bottom, in the positive cycle, DZ2 will get triggered, but there will be a 0.7 drop across this Zener also. So this will be actually Vz plus 0.7. Similarly, in the negative cycle, this Zener Z1 will get triggered, and this is forward bias, so it will be minus of Vz plus 0.7. okay, so additional 0.7 needs to be added here, but okay. So this is about Zener clippers. Now we have something known as clampers also. Clampers generally what they do is they add an additional DC value to the signal. Okay, that is known as clampers. Okay, now here if you see, the DC value is 0 here, the input signal is swinging from plus V to minus V. Now if I have to introduce an DC shift into this circuit, one way of doing it is using a capacitor here, which is known, and then you have a diode and a resistor here. So to analyze these circuits, first you have to see how the capacitor is going to behave, right? For that, the rule is whenever the diode is forward biased, okay, we have to see what happens to the capacitor first. Okay, and then we have to split this into when during the positive cycle what happens, and what happens during the negative cycle. So you have to analyze it in 2 steps. So here if you see, during the positive cycle, this is closed out here. Okay, so since this is diode is closed out here, you can assume that this resistance get shorted out here, so there will be no output voltage out here, right? Because this is a diode, we are assuming it's an ideal diode here in this case. So the moment in the positive cycle, this diode gets shorted, so there is no output available. Okay, and in the negative cycle, okay, and whereas when it is shorted, one more thing would happen. Okay, so initially the moment it is shorted, some current will flow like this, right? So this current will flow here and it will get this capacitor charged to plus and minus. After that there won't be any current in this, and then there will be no output. But the moment it is closed, at that particular instance, okay, there will be a current which will flow like this, and this capacitor will get charged to plus and minus. And in the negative cycle, so this diode is reverse bias, so it is going out of the loop. Okay, so it is not available, but the charge of the capacitor will be retained out here. So you have a plus minus, another minus plus here. So if you see the net voltage from here to here, it will be 2V, okay, minus 2V, like here from here to here 1V, and here to here minus. Okay, so minus 2V. Okay, so in these type of circuits, we are assuming that we have put a capacitor which is big enough so that during this T time it is not getting discharged. So this RC constant is much higher than this T. Okay, so that assumption has been made out here. So if you see during the positive cycle, this diode is forward biased, and and hence the output will be 0. But initially there will be some current flowing in this loop, which will charge this capacitor to since the current is flowing like this, it will be positive here, negative here. In the negative cycle, this diode gets reverse biased, and if you see the net voltage which is here, it is minus plus here. So you will have a minus 2 volt at the output. So if you see what has happened, again this voltage is from 0 to minus 2. So the total peak to peak voltage is 2 volt. It has got shifted. If you see here, the DC operating point for this particular cycle, it is from 0 to minus 2 now, this signal. Instead of V to minus V, it is from 0 to minus V. That means we have added an minus V as an DC, this waveform plus minus V is this. Okay, that is a minus V DC shift we have introduced. Okay, so that is known as clamping the circuit to minus V. Okay, so we have pushed it below the x-axis out here. So if you take one more example here, this is a sinusoidal signal which is given here, right? So now you have a capacitor here, a diode which is placed with cathode on top and a resistor. So during the positive half cycle, okay, so again this diode will be reverse biased. So in the negative cycle, this diode will be forward biased. So the current will flow in this direction, and then this capacitor will get charged to a Vm, which is the maximum signal out here, a Vm. Okay, in the negative cycle, this diode will be reverse biased. So so every positive cycle, every negative cycle, this capacitor is being charged. So we will assume that after first 2 or 3 cycle, plus minus plus here, minus here, Vm will be maintained across this capacitor. So you will find that during the positive cycle, again with the input signal, you need to add plus Vm DC. So this, instead of from minus Vm to plus Vm, now the signal is going to have a DC component which is Vm. So the signal is going to change from minus 2 Vm to 0. Okay, the peak to peak remains same here. Okay, here and here, if you see the peak to peak values is minus 2 Vm, Vm minus Vm is 2 Vm, here also 2 Vm minus 0. Only thing is a DC component of Vm has been introduced. Okay, so we need to see, okay, when we just have to analyze first when is the capacitor is going to get charged through this diode. Okay, so once this capacitor gets seeing the circuit, we need to analyze when is the diode going to remain on, for whether it is for the positive cycle or the negative cycle, and it is we have to assume that the capacitor is going to get charged to a max voltage. Okay, once, and then we put that max voltage as a DC component to get the output waveform. Okay, it will be further clear if we take a few more examples. So this is an input signal 0 to 5, minus 5 to plus 5 input signal, AC signal. I have a capacitor, I have one diode, and I have a minus 3 volt and a reverse biased with this diode. Now when the signal goes to beyond 5 volts, okay, when the signal goes to beyond 5 volts, okay, this diode gets switched on. So there will be current flowing like this here, because this is minus 3 volt, right? So when the signal is going beyond 3 volt, this diode will get switched on. Okay, and finally it will reach 5 volt. Okay, because there is minus 3 already given. So the input signal, the moment it reaches 3 volt and above, this diode will get switched on. Now you have what is the voltage which is going to be across the capacitor? So if you see here, plus 5 volt here and another plus 3 volt here. So this capacitor, the current is going to flow like this. This diode is on, you have plus 3 volt here and you have plus 5 volt here, V max. So in fact across the capacitor it will be plus 8 volt, plus here, minus here. Okay, now in the negative half of the cycle, so if you see from here, okay, what is going to happen? So this capacitor is going to add minus 8, because this is minus here, plus here, right? So this is going to shift the operating condition of the signal by minus 8. Okay, because if, see, plus this diode is going to get forward biased, okay, when the signal is going high. So when it reaches 5 volt here, this is 5, this diode is short, and then you have additional 3. So plus here, minus here. So 3 plus 5, 8 volts get stored in this capacitor. Positive is here, negative is here. So this entire along with this signal, another you got to add minus 8. So this 0 now here, if you see, will correspond to minus 8. Okay, so this plus 5 and minus 8 will become minus 3, and minus 5 and minus 8 will become minus 13. Now the output signal will swing between minus 13 to minus 8. Again, peak to peak is, again if you see here, it is 10 volt. From minus 5 to 5, peak to peak is 10. So that peak to peak will be available here also. Only thing is, it will be, this waveform has been clamped to another minus 10 DC voltage has been added to this signal out here, right? So we'll take one last example, so which will make things slightly more clear. So you have an input signal out here. Again, you have a diode and you have a VN voltage applied here. Now if you see here, when the signal is going in the positive cycle, this diode remains in a negative biased. In the negative cycle, this diode gets forward biased here, right? Because this diode is cathode is pointing top. So when this diode gets positive biased, what will be the voltage across the capacitor? If you see here, right, and you have V1 and also the input voltage, right? So across these okay, so Vmax and V1, they will get added. So it will be positive here and negative here, right? Positive here and negative here. So that is the reason this waveform gets shifted towards the top. Okay, and when this and the voltage corresponding to the minimum position will be minus V1, and the top one will be 2V minus V1. So if you take peak to peak in this case also, it will be 2V, right? This is 2V means Vmax. Okay, Vmax is this, so 2Vmax. 2 Vmax minus V1. Okay, so it is 2 Vmax. Okay, so if you take the difference out here, so it will be 2 Vmax. Okay, so the peak to peak value again remains here. In this case, it is going to get shifted towards the top. Okay, by a value of Vm plus V1. Okay, so it is got shifted onto the top towards the positive side. Okay, so that's all for today. In the tutorial, we'll see some more problems on clippers and clampers. So that things will be even more clear then. Okay, thanks a lot.